or AIDS is a disease that I'm sure everyone here is aware of. In the US alone, more than 1 million people are infected by HIV. And although the US government spends more than $2 billion per year for the research of HIV, still the current therapy cannot cure the disease, can only prevent the growth of the virus. So what makes it so difficult or challenging to cure this disease? Let's look into how our immune system works and how is it in the case of HIV infection. If a virus enters our body, the immune system reacts by producing antibody, and this antibody will bind to the antigen of the virus, and this will activate the virus. The first step in the antigen-antibody binding is that the antibody has to recognize the three-dimensional structure of the virus antigen. In HIV virus, the antigen is the so-called M protein. This M protein has two special traits that makes it so difficult to be neutralized by our immune system. First one, it has a thick layer of glycan, what we call glycan shield. Second, this glycan shield can be modified easily by the HIV virus. This mutation changes the three-dimensional structure of the M protein so that after mutation, antibody fails to recognize the three-dimensional structure of the M protein. This means that in order to develop an antibody-based vaccine against HIV, we need to characterize the exact three-dimensional structure of M protein. And for this, we need a novel analytical method. Recently, our lab have developed the tandem trap immunodeficiency spectrometry in collaboration with Bruker Daltonics. Tandem TIMS consists of two ion mobility spectrometers and is embedded in a tandem mass spectrometer. This gives us additional information about the mass of the protein system. Now, how does tandem TIMS work, and what kind of information can we get from this? We first bring the protein molecule or protein ions from the sample solution into the gas phase by an ionization method. And then a stream of gas flow bring the protein ions into the analyzer of the tandem TIMS. In the analyzer, an interplay between electric field and gas pressure separate the protein ions based on its structure and size. So basically, the information that we get from here is the mobility of protein ions. From here, we can calculate the two-dimensional cross-section. And using a computational approach, which is also developed in our lab, we get the three-dimensional structure of protein. As for the research strategy, I started by studying albumin. It's a quite simple protein which can be found in egg white. I used the albumin as the model system to test the tandem TIMS. In the next step, I moved into a more complex system. Now I'm studying the structural difference between hemoglobin A, which is responsible for the oxygen transport in our body, and hemoglobin S, which is involved in the sickle cell disease. And then step by step, we will move on into more and more complex system while still optimizing the tandem TIMS and also the computational approach at the same time, so that finally we will be able to tackle the three-dimensional structure of the M protein. And this tandem TIMS approach will be also applicable to other glycoproteins that are implicated in other diseases such as cancer. With this, I would like to thank our lab members in our lab, our collaborators, the funding agency, and thank you.